Now I want to try to focus on where this is being applied in different areas of the market. We do see AI being used in a lot of different types of applications. Today, a lot of the AI, most AI work is being done in data centers. And if you look in the data center, you see a lot of Intel and you see a lot of NVIDIA. So for training, the most popular option has been NVIDIA GPUs. The GPUs have a tremendous amount of floating point capability, and then in recent generations, NVIDIA has added what they call tensor cores, which are small matrix multiply units that really boost the multiply, accumulate capability of the chip. In the case of the V100, you can get about 125 teraflops using the floating point, the 16-bit floating point format, albeit at 300 watts. And then NVIDIA also sells a system called the DGX2, which combines 16 of these chips, so now you can get 2 petaflops in a relatively small system. So that's been a very popular option in data centers for training because of the tremendous performance that you can get. Really takes the time required to train even a large neural network down to something fairly manageable. On the inference side, we still see a lot of inference being run on Intel Xeon processors. Data centers treat the inference task like most of their other workloads and try to just allocate it to whatever servers are available at a given time. And so the Intel solution ends up doing a lot of this work. Because of that, Intel has enhanced its newest Xeon processors, codenamed Cascade Lake, with a new technology called DL Boost, which triples the inference performance, the 8-bit integer performance, compared to the previous generation. So, and we'll hear more about that tomorrow, and you can get up to about 18 teraops using this new technology, which is still, falls far short of, what the GPUs are offering, but it is a very generic solution that's easy to deploy. Now, for the data centers that want to focus on something that's more efficient, NVIDIA provides what they call their T4, which is a PCI card that plugs into a standard server and offers 80 teraops at 70 watts. So much more performance than the Intel processor at much lower power. In fact, more than an order of magnitude more power efficient. So if you want power efficiency in your inference, the NVIDIA technology works well. If you want to just be able to deploy it generically across your servers, then the Xeon is a good solution. But the data center market is very big. On the previous slide, I noted it's about at least $4 billion worth of processors sold last year for AI in the data center. So we're starting to see other companies that are very interested in getting into this large and high-margin market. So we see startups like Habana and GraphCore that are very actively pursuing this market. Habana is in production with a chip called Goya, and which targets inference and offers industry-leading performance on networks like ResNet 50 and other types of convolutional neural networks. But we don't really know how well it's going to do on different types of neural networks. There's a large number of different kinds of these deep neural networks, so for very convolution-heavy networks, the Habana architecture looks very good. GraphCore has developed a chip called GC2 that offers floating point capability, so should be good for training neural networks. But we haven't seen any real benchmarks on hardware yet, and we haven't seen any system shipments using the graph core chip, so it's a little hard to evaluate where they are right now. Xilinx has taken their FPGAs and basically pre-programmed the fabric with an architecture that is good at computing neural network calculations. You may know that FPGAs have built-in DSP units, which do a lot of MAC operations. So by combining those together, Xilinx has created what they call the Alveo accelerator, and they've shown that their accelerator can actually outperform NVIDIA's T4 for certain AI inference applications. Huawei makes their own servers, and they've developed what they call the Ascend series of neural network accelerators that are supposed to be shipping soon. The numbers that they posted show industry-leading teraflops per watt, but again, we haven't seen any real benchmarks or other details to really evaluate that technology. And then Wave Computing has developed what they call a data flow processor that targets neural networks as well, which they're planning to both sell in systems of their own design and then also in IP that they will license for other types of applications. And we'll hear more from Wave later today. So, of course, everybody asks, what's the best AI chip for the data center? And the answer is it's complicated. There aren't a lot of good benchmarks for AI right now. And so basically what people are doing is just picking some neural network model and then deciding if they want to test it in a training mode or an inference mode, and then just trying to run that test on some different chips and see what happens. So, ResNet 50 has been the most popular neural network that people benchmark. It's a common image recognition test that was kind of leading in performance a few years ago. Not really widely used a lot today, but it is still a common benchmark. So I've shown here what these numbers can look like, and one of the critical factors that affects performance is the batch size. So you can take, for example, one image and run it through the neural network and then run another image through, or you can take several images and run them all through at the same time. And by running multiple images in a batch, you can increase the amount of parallelism that's available. And for some of these architectures, they really need that extra parallelism in order to achieve their peak performance. So what this graph shows is ResNet 50 inference performance for two products, the Habana Goya product that I mentioned earlier, and then also the NVIDIA Tesla T4. And you can see that both products have lower performance when you use smaller batch sizes, and then they ramp up to their maximum performance as you get up to around 8 or so images per batch. The shape of the curve is a little bit different. You can see that the NVIDIA chip suffers more at lower batch sizes. It's about a 4-to-1 difference, whereas the Goya chip goes down by about 2.5x. So, and some solutions are very flat and have the same performance no matter how many units are in the batch. So, so you really have to understand kind of the whole shape of the curve before you can make any conclusions about performance. So, and the reason that's important is that some applications, you have a lot of data coming through. You can easily make larger batches. Other applications, you may have to process everything one at a time. So depending on your application, you might look at different places on the curve. The other thing I've shown here is the latency. which again, some applications are very concerned with latency. Obviously, if you're trying to make an autonomous car, you may need to make decisions very quickly. Whereas if you're just analyzing photos that have been posted to Facebook to try to decide, whether that's, Aunt Martha or not, the latency doesn't really matter. But for people that are concerned, the numbers here show that, with a batch size of 1, you can get down around a millisecond of latency or less. As you get into larger batches, the latency increases, but, you're still, under 7 milliseconds or so for most of these situations. And then finally, of course, once you benchmark performance, you probably want to consider power efficiency. You might want to consider the cost of the solution as well. So the comparisons are always complicated. It depends on what your application requirements are in terms of performance, in terms of latency, in terms of batch size. It depends on the power and the cost that you're looking at. So there's never any single right solution, and that's why I think we're seeing a lot of companies jumping into this market trying to find some segment or some application in the market that they can compete for. We're also seeing a lot of development at the biggest cloud service providers. These companies are deploying a lot of AI, and so they're buying a lot of these AI chips, probably a lot of that $4 billion I mentioned earlier. And they're realizing that for that kind of money, they could design their own chip. And these companies have a very intimate understanding of the workload requirements that they're running in their data centers, and potentially even the kind of things that are going to be running a year or two from now. And they're able to create designs that are more optimized, to meet the needs of those particular applications, whether that would be, convolutional throughput, whether it would be latency, whether it would be optimizing them for a particular power envelope. So we've already seen Google has now in their 3rd generation of their TPU ASIC design that they've been creating. And what the benchmark shows is that that chip is pretty similar to the NVIDIA V100, the top-end chip, in terms of the training performance. And so, if Google can build that chip for much less than they're paying NVIDIA, that's a good deal for them. Microsoft has been developing something called Brainwave. They call Brainwave, which is based on FPGAs. And the thing Microsoft likes about that is that they can change the architecture anytime, and which they do on a continual basis to try to always improve the performance and the efficiency over time. And they're even able to create new data formats that they can use to try to optimize the performance on their specific applications. Amazon has jumped onto this trend as well. They're working on something that they call Inferentia from their Annapurna subsidiary, and they plan to deploy that later this year. Alibaba and Baidu in China have also talked about working on FPGA-based designs that they may deploy at some point. So there's a lot of work being done in the in-house at these cloud providers, and it's a question of whether these solutions are going to be more powerful than what you can buy off the shelf, and if not, then we may see a swing back toward outside products.